In this video, we're going to go over physical units for a definite integral. So, the question that's going to motivate this video is what kind of units can we give to a definite integral? And we're going to have to think back to derivatives. Remember that one of the points of view we took when we looked at derivatives was that the derivative represented a rate of change. And rates of change have units. So, for example, velocity is a rate of change, and it has the units of distance over time, or length over time. Right? So, in this case, we have an integral. What units can this integral have? Well, let's look at a couple of examples. So let's say that we're integrating velocity, and the velocity is going to be measured in meters per second. Okay, the velocity is a function of time, so t is going to be the time variable, and the units of t are seconds. So the units of velocity are meters per second, and the units of time are seconds. So what units does this integral have? The integral from 5 to 12, so from 5 to 12 seconds, what's the integral of the velocity? And this is how we're going to find the units. It's really simple. We know that velocity has the units of meters per second. There we go. So meters per second. Well, what's this dt? So heuristically what we're doing is we're multiplying this by dt. And remember, when we were doing Riemann sums, v of t represented the height, okay, of the rectangle, and the delta t represented the length. So in this case, dt represents a length will represent the length, quote unquote, of the rectangle that we're going to be finding the area of. And you see this integral is just going to add things up. In other words, we're going to sum up a bunch of areas of rectangles, but now the length of those rectangles are infinitely small, if you can imagine that. So with all that being said, what are the units of dt? Well, remember, it's just delta t. Delta t was just the difference of two t values. So a difference in t's has the same units as t, which is seconds. So there you go. It's just seconds. The difference in time, difference between 2 seconds is still has units seconds. Or I didn't say that the right way, but you know what I'm talking about. So look what happens here. You have meters over second times seconds, and you cancel out the seconds. So you have meters. All right. That's inside the integral, but the integral now tells you to add up a bunch of meters. So finally, at the end of the day, if you add up a bunch of meters, what is the unit going to be? It's going to be meters again. Okay, that was simple. So basically all you have to do is plug in the units and multiply by the units. Plug in the units for the function you're integrating, then multiply by the units of dt. In other words, the units of the variable of integration. So let's do another example, try to drive this point home. S of t, let's consider that to be the function. That gives you the number of classes skipped per month. T is the number of months that have transpired. So let's say t equals 0 is the month that you start taking classes. S of 1 then will be how many classes you skipped at 1. The number of classes you skipped in that month. Okay? Or the rate at which you're skipping classes in that month. For example, S of 2 would be how many classes that you're skipping. Not how many classes, but the rate at which you're skipping classes in the second month. Okay, the rate. So, because of this, per month. So how are we going to do this? Again, just like before, we're going to plug in the units for the function that we're integrating. That's going to be classes skipped. And it's per month, so we'll divide by months. And dt is time in months, or t is time in months, so dt will have the units of simply months. Okay, we cancel those things out. We know that this integral simply means to add up everything that's after it. So it says add up a bunch of classes that you skipped. So the units at the end of the day are classes skipped. Okay, not bad, pretty easy. So one more example. This one's a little more fancy. So let's say L of t is the rate at which oil leaks in gallons per minute. Okay, so here's gallons here. And it's a rate again, it's happening every minute, or it's happening per minute, and t represents time in minutes. So what are the units of this integral? Well, the rate at which oil leaks, the units of that are gallons per minute. Okay? And dt has units of time, which in this case are minutes. So minutes cancel, and you're left with gallons. The integral tells you to add up a bunch of gallons. So the units at the end of the day are gallons. Okay, so that's pretty much it. So you can always find the units of a definite integral as long as you know what the units of the integrand are and the units of the variable of integration. So just to be sure, if you're integrating, so here's an definite integral, a function from f of t of f of the function's f of t, and you integrate with respect to t, this thing, remember, what I've been calling the variable of integration, you need to know the units of that, and then dt will have the same units as that variable. And then you're going to have to know, of course, the units of the integrand. In other words, the thing you're integrating. So once you know those two units, you multiply them together. All this thing tells you to do is add all those units up after you've multiplied them. And so so essentially all you need to do to find the units is multiply the units of f and t together.